Garbage collection in JavaScript is vital for managing memory more efficiently, automatically reclaiming memory that is used by objects that are no longer needed, preventing memory leaks by optimizing performance by reducing memory fragmentation and overhead. In this video, we will discuss minor garbage collection or scavenger in detail. Hi, I'm Rohan, and this video is part of a series of videos where we are exploring how JS manages its memory in detail. So let's get to it. Now that we have a clear understanding of the heap architecture, let's discuss the garbage collection process. Okay, if we take the stack memory, which is much smaller than the heap, there we can just pop the stack frame when we are done with it, as compared to a giant heap where we need to traverse through this huge graph of nodes. And by nodes I mean objects. Still, we at least have a starting point. We know that we can access references to the root nodes through stack, and once we get to the root node we can access the references to its child nodes, then its child nodes, and so on. Eventually we cannot access certain nodes, but we can safely assume that these nodes or objects are no longer needed, so the garbage collectors can free this part of the memory. Now the problem is, whenever we run out of heap memory, we need to traverse this huge graph of nodes and remove the unneeded objects. What this means is that we need to stop our application process and perform the garbage collection every time. This will slow our entire application down noticeably or even may crash it. So this is where V8 applies a very clever strategy. The V8 divides its heap into generations. There is a young generation, which can further be divided into nursery or intermediate subgenerations, and an old generation. But why does it do that? The V8 follows this design based on a hypothesis. This hypothesis states that young objects are much more likely to die than older objects. And this hypothesis is known as generational hypothesis, which means that in most cases, objects that have been allocated memory becomes unreachable almost immediately, which are then garbage collected. The young generation occupies a much smaller region of memory, and garbage collection happens here much more frequently as compared to old generation. This gets rid of most of the new short-lived objects, and we are left with older objects. These older objects occupy a different region of memory which is relatively much larger, and in this space the garbage collection can happen less often, so the overall application process won't slow down much. The V8's generational heap leverages this fact about objects' different lifetimes. Objects are initially allocated in the nursery. If they survive the first garbage collection cycle, they are categorized as intermediate but still remain as young generation. If they survive yet another garbage collection cycle, they are recategorized as old generation and are moved to old space, where they are eventually garbage collected. And the young and old generation objects utilize different garbage collection strategies. The young generation utilizes minor garbage collection or scavenge, which is a much faster algorithm, but it consumes more space. The V8 allocates a much smaller space for young generation, and hence the algorithm runs much more frequently. The old generation utilizes major garbage collection or mark sweep compact process, which is a much slower algorithm, but it utilizes various methods to compensate for the issues caused by its slowness. Let's talk in depth about scavenger garbage collector, which operates in new space. We start our code's execution, and at this point in time, the from space inside new space is empty. And at some point in time, the code creates a new object. And since there is space inside from space, a memory is allocated to the object, and that corresponding memory reference is updated in the stack memory. This happens several times, and at each time memory is allocated and the memory reference is updated in the stack or in the parent object via the stack. Now, next time this happens, the from space is full. So the garbage collector starts working. It goes through the stack memory to build an initial list of references to scan. Any reference to an object in from space will be added to this list, which means a reference in stack memory that points to from space will be added to this list, which is called a root node, by the way. or an object in old space or large object space that contains a nested object reference that points to from space will be added to this list. From now on, whenever I say node, I mean object. It picks up a reference from this list and scans from space for the node. When it finds the node, it checks if it's a nursery node or not. If it is, then it is copied to to space and marked as intermediate node. If it is not, then it is already an intermediate node and it is copied to old space and marked as old generation. Then the copied node is checked if it contains any references that points to from space. If it does, then those references are added to the reference list that the garbage collector is using. After that, another reference is picked up from this list and the process repeats until all the nodes are scanned using these references. Now, at this point in time, we know that the garbage collector has scanned all the nodes that it could reach inside from space. So, any nodes that are unreachable after this must be dead objects, or these are objects which are not in use anymore. Hence, in the next step, all the memory allocated to these dead objects are deallocated and the entire from space is cleared. After that, the spaces are swapped, which means that the from space becomes to space and to space becomes from space. Then our main process resumes, which means that memory is allocated to the pending object and its corresponding reference is updated in the stack or in the parent node. This is the entire process of scavenger, also known as minor garbage collector. Let's visualize the scavenger process using an animation. When a process starts, whenever an object is created, it is allocated memory in the from space and the corresponding reference is updated in the stack or in the parent node. When the from space is full and the allocation fails, then the garbage collection process starts. It selects a node that it can find via references one by one and copies it to space if the object is nursery or old space if the object is intermediate, and recategorizes the object to intermediate or old respectively. And of course, the references to the copied nodes are updated in the stack or in the parent nodes. After the garbage collector goes through all the nodes that it can find and copies them, it clears the from space, and from space becomes to space and vice versa. Then the process resumes and the pending object is created in the from space and so on. At the end, the process is complete and both the stack and heap memory is released. To summarize, we discussed garbage collectors and JavaScript's clever utilization of generational hypothesis to manage new objects and old objects differently, utilizing different strategies to manage each of them separately. How minor garbage collector is used to deallocate most of the newly created short-lived objects by running the garbage collection process in a separate segment of heap memory called the new space. We also looked at the scavenger algorithm in depth and visualized it with an example. But we haven't discussed the major garbage collector, the mark sweep compact process. So we will discuss this in the next video. Thank you for your time. Have a nice day. Namaskar.